right, so this is lecture 9, and this is the applications of exponential and logarithmic functions. So we had a couple questions a couple lectures back, and it had to do with some of our interest questions, and we couldn't solve some of those equations because we did not have the inverse of an exponential function. But now that we do, we can solve those equations. So for example, Mr. Adams invested $1,000 at 4.5% compounded continuously. How long will it take his money to double? All right, so we know that the compound continuously compound interest formula is A equals PE to the RT. In this particular question, we know that A is going to be 2,000 because we want our amount to double, and he invested 1,000. So doubling that would be 2,000. Our rate is 0.045. And we want to know the time that it takes for it to double. All right, so we're looking for T. All right, so I have 2,000 equals 1,000 e to the 0.045 t. All right, so the first thing I'm going to do is I'm going to divide by 1,000. And I get 2 equals e to the 0.045 t. Now, for me to find what t is, I need to bring t down in front, and the only way I can do that is by our laws of logarithms. And since my base is e, I'm going to use natural log. And in general, I always use natural log, unless the base just happens to be 10. All right, so I'm going to take the natural log of both sides. So natural log. So I have a natural log of 2 equals, now my law of log says I can bring the exponent 0.045t out in front. So I have 0.045t natural log of e. Now we know that the natural log of e is 1. And I'm solving for t, so now what I want to do is I want to divide natural log of 2 by 0.045, and that will give me t. So t equals 0.045. Let's try that one more time. T equals natural log of 2 divided by 0.045. And that is going to give me approximately 15.4 years. And my math lab will tell you how many decimal places to round to. What if his money is invested at 4.5% compounded quarterly? So then we need to use the formula A equals P1 plus R over N to the NT. All right, so we need to use a different, it's not compounded continuously. All right, in this case, again, my R is going to be 0.045. My A is still 2,000. My P is still 1,000. And it's compounded quarterly, so that means my N is 4. And I'm still looking for T. So I'm still looking for my time. So we're going to plug all that in. 2,000 equals 1,000. 1 plus 0.045 over 4 to the 4t. I'm going to do the same thing that I did the first time. I'm going to divide by 1,000. So I have t equals, what is 0.045 divided by 4? Anything nice? Yeah, not really. So it's 0.01125. And if I add that to 1, I have 1.01125 to the 4t. And now, I'm going to take the natural log of both sides because I want to solve for t, and I need to bring 4t down in front. So I have natural log of 2 is equal to, excuse me, natural log of 1.01125 to the 4t. I bring the 4t out in front, natural log of 1.01125. And I'm solving for t. So now I'm going to divide natural log of 2 by 4 and the natural log of 1.01125. So t is equal to the natural log of 2 divided by 4 natural log of 1.01125, which is approximately 15.49 years. All right, so just a little bit longer than compounded continuously. All right, so the next question is present value. So the present value is, okay, I am, and this is the example that they're going to give us, I'm going on a trip in so many years. How much do I need to invest if I know the interest rate so that I can go on that trip? All right, that's what the present value is. What do I need to invest? So Sam is a freshman in college. For graduation, he wants to take a backpacking trip to Europe that he estimates will cost $6,000. Assuming he adds no more money to his fund, how much must he invest now to be able to pay for that trip in 4 years if the account earns 4% compounded semi-annually? All right, so again, we want to use A equals P1 plus R over N to the NT. All right, so we want to end up with $6,000. So A equals 6,000. We are looking for P. We're looking for the amount we want to invest. My R is going to be 0.04. My T is going to be 4 years. And N semi-annually, so it is 2. All right, so let's see. Go ahead and plug all that in. I have 6,000 equals P. 1 plus 0.04 over 2 to the 2 times 4. All right, so I have 6,000. Topo snoring back there. 0.04 divided by 2. Plus 1, 1.02, raised to the 8th power, 2 times 4. Let's bring that down a little bit. Oops. Sorry. Okay, give up. All right, so really all we need to do is divide by 1.02 to the 8th power. So P is equal to 6,000 divided by 1.02 to the 8th power. Trudy, can you give me a second? 6,000 divided by 1.02 to the 8th power. All right, so they are giving me approximately $5,120.94. All right, and now they want us to do the exact same thing, except compounded continuously. So I have A equals PE to the RT. So I have 6,000 equals PE to the 0.04 times 4. All right, so P is going to equal 6,000 E to the 0.04 times 4. And I will just give you as a hint, do not round anything until your very last answer. So you shouldn't put it in your calculator till the very end because you will get rounding errors. So 6,000 divided by E, and make sure you put all of these in parentheses or it will, the calculator will not recognize your order of operations and it will think that you are multiplying, you're going to do 6,000 divided by E to the 0.04 and then multiplying it by 4. But you want the power to be to 0.04 to the 4 or just multiply by 0.08. All right, and I'm getting $5,112.86. All right, so that is present value. How much do you need to invest to get the amount that you want now? All right, exponential growth. All right, so the amount, so I have some quantity and the amount of that some quantity present at some time. All right, so you have a growth constant, K. And if something is growing, you've heard of it, growing exponentially, I have a exponential growth function where Q naught is the initial amount. All right, so if I have my function Q of t and I have the initial amount, I plug in time 0, then I get Q of 0, E to the, doesn't matter what K is, and my time is 0, K times 0, it's always going to be 0. I'm going to get E to the 0, and E to the 0 is always 1. So you're going to get Q naught. All right. So you're going to get the initial amount. All right. K is called my growth constant. All right. So I have an exponential growth function that looks like Q naught E to the KT. All right. If you look at it, it looks like PE to the RT, right? Q naught E to the KT, all right? But your K is your growth constant. T is still your time. Instead of the amount invested, you have the initial amount, right? So the initial, depending on what it is, like the population, the initial amount of grams, just depending on your, it just depends on, it depends on the type of model, what it's modeling. All right. So first example, a colony of viruses is growing exponentially. There were 500 viruses at 10 a.m. and 20,000 at 3 p.m. Find a model for this growth, okay? So a virus is growing exponentially, 500 viruses at 10 a.m. So my Q naught, my initial amount, is 500. Now, the initial time is 10 a.m. So time 0, t equal to 0 is at 10 a.m., which means 3 p.m. is how many hours later. Oh. So that is 5 hours later. So T equals 5. All right, and they have 20,000. All right, so if I were looking at trying to set up my initial function, Q of T, all I have is the 500 and e to the k times 0. Well, we already know that. Whoa, Triggy, you messed up. There we go. So what I'm going to do now, and that's just going to shoot me out my Q naught. So that's not going to be very helpful. But now what I'm going to do is I'm going to put in this next point. I'm going to plug in T equals 5 for 20,000. So that can give me my growth constant K, right? So I have 20,000 equals Q naught, which is my 500, e to the K, and my time is 5. All right. All right, so my only unknown at this point is K, and I can solve for K, and then I can come up with my model. All right, so I'm gonna divide both sides by 500. And let's see, how many zeros do I get rid of? And 5 goes in 40 times. So I have 40 equals e to the 5k, right? I need to solve for k. So what I need to do is I need to take the natural log of both sides. So I have the natural log of 40 equals the natural log of e to the 5k. I'm going to bring the 5k out in front. And remember, the natural log of e is 1, and k is equal to the natural log of 40 over 5. And let's move this up here. And this up here. So now we can write our model because we have our Q naught and we have our K. So Q of T is equal to 500 e to the KT. And our K, again, is natural log of 40 over 5 to the T. All right, so when we're looking for a model, the things we need is our Q naught, our initial amount, and our growth constant, right? And then our variable is T time. All right, the next question is how many will be in the colony at 6 p.m. approximately? All right, so we know that time 0 is at 10 a.m. So we need to figure out what time is at 6 p.m. At 6 p.m., T is equal to 8. All right, so let me copy this. And we just want to find Q of 8. So Q of 8 is equal to 500 e to the natural log of 40 over 5 to the 8th. All right, and we are going to plug that into our calculator. And again, make sure you get enough parentheses in here. 8 times natural log of 40 divided by 5. And I came up with approximately 182,922. All right, now it says how many will there be at 8 p.m. and they want to know exactly. So in other words, they don't want an estimate, they want to know exactly. So we're going to use like our laws of logarithms to figure it out. So at 8 p.m. T is equal to 10, right? So Q of 10 is equal to 500 e to the natural log of 40 over 5 times 10. All right, so if I have 10 divided by 5, that gives me 2, 1/2, right? Oh, 2, right? So let's rewrite it like this. 500 e to the 2 natural log of 40. But because I have the natural log, I can raise that to 40 squared. All right, now if I have e to the natural log of something, then I can, that is the same thing as just what's inside. So that is the same thing as 500 times 40 squared. 40 squared is 1600. So I have 500 times 1600 and that is 800,000. Now, I think if you plugged it in right here, you should come up with the exact same thing. It shouldn't give you an approximation. It should give you exactly the same thing. Right, so if I plugged in 500 e to natural log of 40, it should give me the same thing. Yeah, it does. But just so we could see how we did it. All right, next question. According to the Census Bureau, the Hispanic population in the United States is expected to grow by 2.1% per year between 2000 and 2050. If the Hispanic population was approximately 38 million in 2000, find a model for that growth. What should the population be in 2015? So we have two questions. We need to find Q of t equals Q naught e to the kt. And then we want to use that to find the population growth in 2015, right? Why don't we rewrite it as P of t equals P naught? So it's a population growth. Same thing, right? Let's let P of t be the population 10 years after 2000. So 2000 equals t equals 0. And we're going to put it in millions so our numbers aren't so large. So again, P of t equals P naught e to the kt. So when t equals 0, so that's the year 2000, P is equal to 38, right? So I have P of t is equal to 38 e to the kt, right? That's my population. Now, when t equals 1, my population is 38 million plus an additional 2.1%, right? So 38 times 0.021 or 38 times 1 plus 0.021 or 38 times 1.021, right? Right, so it's growing by 2.1%. So I have 38 million the first year and then 38 million plus the additional 21% the next year, okay? All right, now, if I were modeling, if I were plugging in P of 1 to my model, and I know that it looks something like this, right? Because P naught is 38, because that's the initial amount. So P of 1 looks like 38 e to the k times 1, right? But we also said that that population was equal to this, 38 times 1.021. All right, so what we said before is if I want to model, a population growth or a growth function, I need the initial population and I need the growth constant, all right? I have the initial population, I don't have K. So what I'm looking for right now is I'm looking for K, all right? So now what I'm gonna do is I'm gonna set these two equal to each other, right? So I have 38 e to the K, because K times 1 is just K, equals 38 times 1.021. All right, I'm gonna divide both sides by 38, and I'm gonna get e to the K equals 1.021. Tiny, do you need down? All right, I'm gonna take the natural log of both sides because I need to solve for K. So I have natural log of e to the K equals natural log of 1.021. K down in front, and the natural log of e is 1, so K is equal to natural log of 1.021. So then my model is P of t equals 38 e to the natural log of 1.021 t. All right, so I have my model, all right, where again, t is the years after 2000, and this is going to give me the population in millions. All right, now they want me to find the population in 2015, so that is going to be when t is exactly 15. All right, I'm going to erase some of this because I am out of room. So P of 15 is equal to 38 e to the natural log of 1.021, and this is just a matter of plugging it into your calculator, and you're going to get 51.9, and again, this is in millions, so 51.9 million. All right, so that was a different type question to come up with K, right? Now, so that was an exponential growth. Now, and I didn't graph this, but whatever this Q naught is here, and I should have done this, I'm sorry, so we're going to kind of go back. Q naught is going to be your initial point here, and it's just going to grow exponentially. Now, what we're going to have is we are going to have a decay. All right, your Q naught here, and it's going to look exactly the same, except for your K is going to be negative, right? So if you remember graphing your exponential functions, if it was negative, it was going to be right? So remember when we graphed our exponential functions, they looked like this. Right? So this time, again, it's going to look exactly the same, except for our k is going to be negative. All right, now, the other thing that we want to talk about is the half-life. All right, so the half-life is going to be the amount of time for it to be, say, like half the population, right? Or half the amount of the time that it takes for 1/2 of the original amount to decompose. Let's write that definition. Half-life is the amount of time it takes for exactly 1/2 of the original amount to decompose. So you'll see this a lot with carbon dating. All right, so here we go. So example, the half-life of radium-226 is approximately 1,620 years. Find a model for the amount of radium after T years. So again, Q naught E to the KT, right? Now, they do not give us the initial amount, all right? They just know that it takes 1,620 years. So I know that if I have the original amount is Q naught, then half of Q naught takes 1,620 years, all right? So I don't know how big Q naught is. I just know that that's how long it takes. All right. So let's see. Now, since I can cancel Q naught, I will end up with just one variable and to be able to solve for K. All right. So I'm going to cancel out Q naught. And I have 1/2 equals E to the 1,620K. I'm going to take the natural log of both sides. Natural log of 1/2 equals natural log of E to the 1,620K. All right, natural log of E, again, is 1, so I'm going to bring this 1,620K out in front, times natural log of E, which is 1, so I get 1,620K equals natural log of 1/2. Now, let me remind you that natural log of 1/2, I can use my laws of logarithms as natural log of 1 minus natural log of 2. Now, natural log of 1 is 0. So negative natural log of 2 is going to give me something negative. All right, you can leave it as natural log of 1/2 if you want to, or you can write it as negative natural log of 2. All right, I think for right now, I'm going to write it as negative natural log of 2 so that we can just keep in our head that I'm going to get a negative K because this is a decay. K is negative natural log of 2 over 1,620. So my model is going to be without Q naught because they did not give me enough information to find Q naught. All right, so I have Q naught E to the negative natural log of 2 over 1,620 K. All right, it asks me now how much will be left in a 400-gram sample after 810 years. All right, so now they're saying, okay, I'm given an initial amount of 400. and my time is 810 years. All right, so I can plug in Q naught, and oops, I forgot my T here. And I can plug in my time T. So Q of T, is equal Q of 810 is equal to 400 e to the negative natural log of 2 over 1,620. Man, let me redo this right here. That was my K. All right. To the T, and my T is 810. All right, and that is going to give me approximately 400 e to the negative natural log of 2 divided by 1,620 times 810 in parentheses. 282 grams. All right, so now it asks me how long will it take for 20% of that sample to disintegrate. All right, so if 20% of it has disintegrated, then how much would be left? So that would be 80%, right? So I want what's left over to be 0.8 of that 400 gram sample. And the initial amount is 400. And I still have e to the negative natural log of 2 over 1620. And this time we are looking for time t. All right, so my quantity was 80% of the initial 400 grams, all right, because 20% of it disintegrated. All right, again, I'm gonna divide by 400, so I'm gonna end up with 0.8 equals e to the negative natural log of 2 over 1,620 t. Take the natural log of both sides. And that's going to bring the exponent in front, and the natural log of e, again, is 1. So I'm going to get negative natural log of 2 over 1,620 times t. So t is going to be natural log of 0.8 over the negative natural log of 2 over 1,620. So let's just plug that in. I get the natural log of 0.8 divided by the negative natural log of 2 divided by 1,620. Whoops. Let me try that one more time. Natural log of 0.8 divided by the natural log of 2 divided by 1,620. And I'm getting 521.52 years. So approximately 521.52 years. It may have been easier to do this if you multiplied by the reciprocal, but either way, it should work. And that is the end. All right, so we had present growth, that might have been new, exponential growth, exponential decay. All right, so that is the end of lecture 9.